This is a special session. The last few days we've been hearing Antonio Lazcano in many of the sessions. We've appreciated his scientific breadth, his wisdom, his humour. But this afternoon we're to hear him lecture on his personal area, where he's an absolute international leader. He's a professor at the National Independent University of Mexico. He's the president of the International Society for the Study of the Origin of Life. He's also a researcher into the chemical basis for the origins of life. He's an educator, a scientific journalist and a teacher, a writer of textbooks for schools and the public, for the general public. So, ladies and gentlemen, we're privileged to hear Antonio Lazcano on this topic. Thank you.
Thank you, Chris. Thank you very much, Chris, for the presentation. Ladies and gentlemen, thank you very much. I have to say that for me it's an absolute privilege to be back in Australia, to be here in this hall, and to have the chance to share with you some of my ideas on the origins of life, which I decided was good to put in the context of evolutionary theory, because this being a festival of ideas, one should underline that the idea of evolution is one of the greatest intellectual achievements of Western civilization. And from there it spread worldwide in a way that it's absolutely amazing. One thing that has to be said right ahead is that whenever we think about evolution, the great name that comes into mind is that of Charles Darwin. But one should be very much reminded that, in fact, the idea of evolution is older than Charles Darwin, is older than the origin of a species. In fact, there is a lengthy chronology of the idea of change in nature that started not among biologists, but in fact started among astronomers, when Kant in 1786 proposed the idea that the solar system itself was the outcome of the collapse of a nebula of interstellar gas that somehow gave rise to the sun and the earth. And later on, this idea was actually put in mathematical terms by the Marquis de Laplace, who made that very famous remark when Napoleon told him, "I don't see the word God mentioned in your book." And the answer was, "Sir, this is a hypothesis. I do not need to explain the origin of the solar system." But the idea of evolution was already in science. And then, of course, we know of Darwin and his publication in 1859 of The Origin of Species. But it was preceded, in fact, 50 years by the work of Jean-Baptiste de Lamarck, who proposed a book called La Philosophie Zoologique, in which also the idea of evolution, transformation of a species was proposed. Lyell, who was a professor of Darwin, spoke about the evolution of the surface of the Earth. Sadiq Carnot and Thomson spoke about how you can have a system that is isolated in thermodynamically, not able to exchange matter and energy with the surroundings, and then goes to increase entropy, to increase disorder. So here we have the idea of time in thermodynamics, the idea of evolutionary thermodynamics. Spencer was writing of language evolution, and Malthus, which some of my more leftist friends don't like to very much, was actually speaking about evolution of human populations. Renan in France was speaking about the evolution of religions. Marx and Engels spoke about socio-economical evolution, the evolution of productive systems. So what we really see is that the 19th century is the time in which the idea of change, of evolution, of modifications in time becomes deeply ingrained in Western culture. In this sense, Charles Darwin should be seen not as the starter of the idea of evolution, but rather as the culmination of 19th century thoughts on evolution. Now, by one of those extraordinary things that happened in history, as I already mentioned, Jean-Baptiste de Lamarck published in 1809 his book of La Philosophie Zoologique, and in a way this book became the birth certificate of Charles Darwin, who was born precisely on 1809, and who was like to self-describe himself as, in fact, a follower of Lamarck. Now, whenever we think about Darwin, we think about this very venerable English gentleman, a member of the rural gentry that came from a very distinguished family and changed forever the way we look at life, the way we look at ourselves. But the fact is that we shouldn't forget that Darwin once was a very young fellow. And when he was a young fellow, he didn't happen to be a very distinguished student. So much, in fact, that his family, his father especially, had very deep concerns about the family reputation because of his very poor achievements in school. Now, Darwin came from a family that on the father's side had very, very distinguished physicians, especially his grandfather, Erasmus Darwin, who was a larger-than-life figure. He developed a number of very interesting ideas on therapeutics, on the use of electrical discharges to cure a number of ailments, so much to the point that if you read the dedication of Frankenstein by Mary Wollstonecraft Shelley, you will find out that it is dedicated precisely to Dr. Darwin, whose researchers have demonstrated the truth of what is described in this book. He made a tremendous impact in English society. His son, Robert Darwin, who was a very stern gentleman, as all Englishmen, he was very fond of gardening, of course, but he was very stern with his children. And he finally decided that both Charles Darwin and Erasmus, his brother, should be sent to the best possible medical school in the United Kingdom. So they were sent to the Edinburgh School of Medicine, where one of the things that was for me it's very natural, not for my American colleagues, is that you didn't have to be ordained to be a teacher in that university. Charles Darwin went there with his brother. He was there only for 6 months or so, and we know exactly why he left medical school. First of all, he could not tolerate the idea of blood. The idea of smelling blood, of looking blood, made him absolutely ill. Secondly, he could not cope with the weather in Edinburgh. Lovely people, but horrible weather. And thirdly, he said, I cannot accept the idea of getting up at 5 in the morning, have a Scottish breakfast, and then go to lectures. So he left school, and the family decided, well, if you're not good as a physician, you might as well be good as a minister. So he was sent to Cambridge to study divinity. He was not exactly what you would call an outstanding scientist, and then thanks to family connection and family money, he got a position as a naturalist in the Beagle under the leadership of Captain Fitzroy. Now, we know exactly what Darwin's feelings were when he boarded the Beagle, because he wrote on the very first day in his diary, this place is crowded, it's very smelly, it moves a lot, it's very noisy. I cannot see how I can tolerate being in this boat for 5 years. And the boat was still tied up to the piers of Plymouth. I mean, he had all the elements to be a failure, but then, with his extraordinary powers of observation, with an extraordinary boiling brain in which everything was being sucked and connected and so on, he finally came back to England, went back to England, decided that London was not the place for him to be, moved into Down. He married his cousin, which is something that always is prone to jokes in Mexico, I have to say. He married his cousin and settled there and became, in many ways, the reluctant revolutionary. Darwin, for me, is the best example of how we should not ever have a prejudice about the men and women that can change life, that can change society. He was the less outstanding revolutionary, and nevertheless, he changed forever the way we see ourselves and the way we see life on Earth. And of course, all of you know that after much pressure from his friends, after receiving the letter from Wallace, who came out with a similar idea on natural selection, he published in 1859 the famous Origin of a Species. And as one of his peers remarked, you might have as well published a book on pigeons, because the book is full of examples taken from how you can raise pigeons or horses or sheep or cows and select features that you find interesting for different purposes. The basic idea, however, behind the Origin of a Species is a very simple one. It's the fact that you can understand the unity and diversity of life thanks to a common origin and to the mechanism of natural selection. It's a very simple but a very powerful idea. So simple, so powerful that Huxley, one of his best friends, once said, it's a pity that idea didn't occur to me. I think it's the best praise one can have for a colleague, for a friend. Such a simple idea, and it was brewing in his mind for a number of years. Now, if you read The Origin of a Species, you will find that at some parts it's very dense, it's full of detail, it can be a little bit complicated to enjoy, but one part of his writings that I enjoy enormously is reading his notebooks. And I like them because there you can see the way his mind was actually working. This particular page I'm very fond of, for a very simple reason. It says, I think. And this, I think, summarizes in a very simple phrase the doubts, the certainties, the questioning that he was undergoing, and then he draws this hypothetical phylogenetic tree in which he explains how you could have divergence of different species from a common ancestor. And then there is this other page from one of his notebooks that I'm particularly fond of, thinking of the origins of life, because here you have 3 hypothetical species, drawn in bold lines, and just looking at the similarities, Darwin proposes, okay, so these 2 must have diverged later on from the ancestor of these other species. And he has in broken line a hypothetical phylogeny. And I like the idea of a broken line as a hypothesis of evolutionary relationship, because that's exactly what our phylogenies are. Whenever we construct a phylogenetic tree, what we are proposing is a hypothesis of evolutionary relationship that may be correct or may be wrong. And we have to be, in biology, extremely eclectic in the sense that we take all possible data on behavior, on molecules, on biogeographical distribution, on morphology, in order to assert or not our hypothesis. Now, the other thing that you can see from these 2 pages is that, from Darwin's notebooks, is that although he failed medical studies, he did keep physicians' handwritings until the very end of his life. It's quite an ordeal to go through his notebooks and try to understand them, to the point that there are some words and phrases that have always been left with a question mark because we really don't know what he wanted to mean. Nevertheless, I want you to please compare these phylogenetic tree with the one that is drawn on the basis of the comparison of a molecule that is involved in the replication of retroviruses, specifically the HIV virus. We can construct, using exactly the same basic principles that Darwin developed, we can come out with a history of the HIV virus, which is, of course, a major pathogen, which has caused a tremendous change. It has tremendous socioeconomical consequences, has led to the isolation of people in a terrible way, and so on. And here what you have is how we can actually reconstruct the different the relationships of different strains of the HIV virus. We can actually put the place of what is probably one of the oldest HIV virus that we can recognize from a blood sample that was kept by chance in Belgium from 1959 until today. We can relate the HIV virus to other retroviruses. We can deduce without any problem that, in fact, the 2 epidemics that we are witnessing comes from 2 different jumps that retroviruses made from different primates into our own species. And this is showing, in fact, how, using the methodology developed by Darwin first, that retroviruses evolve, diversify, and can overcome the species barrier. It's very complicated to get a visa to visit Australia. Viruses don't need a visa to jump from one species into the other. Viruses are the perfect way to actually go through frontiers undetected in many ways, through the taxonomical frontiers that separate different living entities. And this particular tree shows very clearly that evolutionary theory is not something that is related only to the disappearance of dinosaurs or to the emergence of land plants. Evolution is something that has to do with our everyday life, because it's true that we can reconstruct the evolution of a retrovirus like the HIV one, but it's also true that using evolutionary criteria, we can actually develop therapies to control the development of the disease in people that are infected. So quite clearly, evolution is not something only for textbooks. It has to do with our everyday life. And there's another wonderful example of this, which has to do with bacterial resistance to antibiotics. I made the experiment today in a pharmacy, in a chemist office nearby. I went and asked him, can I have an antibiotic because I have some diarrhea? I have no diarrhea, I have to say, but I wanted to test how it works in Australia, and the question immediately came from the chemist, can I see your prescription? And I say, I have none. And he said, well, I'm sorry, then I cannot give you any antibiotic. If you do the same experiment in Latin America or in a number of Asiatic countries, you will immediately get the antibiotic you need without any prescription. In other words, there are a number of societies in which the people can administer themselves an antibiotic, which is normally used in a very unprofessional way, without any medical control, not for the time that's necessary to actually complete the scheme, and the result is that we are developing resistance to antibiotics. How does that happen? Well, assume that we have a bacteria that begins reproducing, and all of a sudden you have a mutant just by chance, or because it acquires a virus that carries on the gene that can decompose a given antibiotic, and it will not prevail among the population of other bacteria, among other things because it has no advantage. But the moment we apply to this colony of bacteria, whether in our guts or whether in under laboratory conditions, then what immediately happens is that the bacterial strains that are resistant to an antibiotic will be selected. It's a very simple mechanism, and the basic point to underline here is that natural selection has no foresight, no goals, it only produces result. That is the basic idea behind natural selection. And of course, in this case, we can reconstruct the genealogy of these different strains of bacteria, but in biology, in historical times, in a historical perspective, genealogy means phylogeny, and that means reconstructing the history of life on Earth. And we actually can do so very easily, and by comparing, for instance, the molecules involved in the synthesis of proteins, we have come up to recognize that at a cellular level, life on Earth is not divided in plants or animals, is not divided in, let us say, in prokaryotes or eukaryotes only, but it's actually divided into three major groups that are called the bacteria, like the ones that produce the yogurt that you had for breakfast, the archaea, which are basically fastidious prokaryotes that like to live, most of them, under extreme conditions, and eukaryotes, which is, of course, the branch of the tree in which ourselves and most our relatives and best friends are located. I have to say that I have said here that these are major groups. There is a word that is used by a very distinguished microbiologist, Carl Woese, which is domains. The domain archaea, the domain bacteria, and the domain eukarya. But as a Latin American, I always feel a little bit uneasy when Americans use the word domains. So let me just refer to them as lineages, three basic lineages. One of the things that has emerged very quickly from this overall picture of the biosphere is that most of the diversity that we see of life on Earth is dominated by microbes. Unseen microbes have been the dominant form of life on Earth since it started more than 3.8 10 to the 9 years ago until today. Prokaryotes, bacteria, and archaea, and many eukaryotic microbes are in fact where we find the greatest diversity on life. And without them, we would not be here. You can take away the fungi, you can take away humans, you can take away other animals, and the biosphere will thrive on without any problem because prokaryotes have all metabolic abilities to go on. If you take away the prokaryotes, life on Earth will not go on for more than few 1,000 years or million years at the most. So clearly this is the most resistant, the oldest forms of life that we actually have to study. We want to understand how did life appear on Earth and how was it maintained during several millions or billions of years. Now, here we immediately face a problem. If we draw a timeline with the origin of the solar system and of the Earth at 4.610 to the 9 years ago, and the present here to the right. One of the problems that we immediately recognize is that at the very beginning, the Earth was probably very hot. It was a very turbulent place with comets and meteorites falling all the time, with very unstable continents, very likely too hot to have water, liquid water on the surface. So if we have no water, it's very difficult to imagine how we could have life appearing. On the other hand, if we go back in time, and I have to say the Australians are extraordinarily privileged because some of the oldest evidence of microbial life comes from here and from the work of extremely distinguished scientists like my friend Malcolm Walter and so on. We can be quite sure that 3.510 to the 9 years ago, there was already a thriving biosphere composed mostly of prokaryotes. We have very good evidence that life was a very, very dominant on the Earth since 3.5 years to today.